Okay, we've just completed the multiple choice section of the test, and now we're going to review the part B2 and the part C, which is the free response section, about 35 points beyond the 50 multiple choice questions you've had. And let's get started with number 51. Our answer is going to go into a booklet, but we're just going to read off this question right here. So number 51. What is the mass of potassium nitrate that must dissolve in 100 grams of water to form a saturated solution at 50? Okay, so I'm looking at this question here, and they're asking for grams that must dissolve in 100 grams of water at a certain temperature. So this is reminding me about a solubility table. Table G is going to be our friend here. Now, when you deal with a solubility table, you have to look at how much water we're dealing with. Very important. Of course, how much temperature, okay, and of course the key word here that got me thinking about table G, okay, is the word saturated. And you should have learned that saturated means that on these tables that you are on that line. That's the max amount of solute that can dissolve at a certain temperature. So what we're going to say is we're going to go to table G, we're going to find potassium nitrate, and we're going to see, okay, how many grams it takes for it to get on that line exactly at 50 degrees Celsius. Table G, here we come. Okay, so we're here at table G, and we're looking for potassium nitrate, and there's my curve here. And notice this is solubility per grams of 100 grams of water. So if that grams of water was different, we would have had to make an adjustment here, like cutting it in half or doubling, depending upon how much water. Because solubility is based upon how much water you have, and of course the temperature of the solvent. In any case, back to our question. They said if I have potassium nitrate, which is this curve, and now I suggest when you're taking a test, okay, especially with this curve, draw on the line here. Okay, make it very clear that this is the line you're dealing with. So when you're dealing with this line, I suggest you draw on it, just so you don't confuse the other lines in these questions. You're going to have a fresh reference table for the exam. Okay, now at 50 degrees Celsius, okay, we want a saturated solution. How many grams does it take? So at 50, I'm going to go all the way up on this line, straight to the line, till I hit this point right here. Now, of course, I have written all over it, so I want to look at it now. So at 50 degrees Celsius, it appears to me that I'm a little less than halfway between 80 and 90. So my guess would be 84 grams, okay? And again, 84 or probably 82 grams would be accepted. They usually do plus or minus 1 here. My guess is about 84, not that 82 there. Okay, so I would suggest an 84 or 83. My guess is 84. So it takes 84 grams. Now, these grams right here, of course, are the grams of the solute. So this is 84 grams, my guess, okay, in this question, that it would take to get right on this line. Supersaturated above, unsaturated below. So in my answer booklet, I would write 84 grams. Okay, and they would give you probably plus or minus 1 there. Okay, so number 52. Identify the type of chemical reaction represented by the equation. Okay, well, I'm looking at this equation, I'm seeing a classic single replacement. The aluminum's replacing the copper. Okay, and you can see that the aluminum's changing places. Single replacements are classic redox reactions. Okay, another way to look at a redox reaction is to see if the oxidation numbers are changing. Standalone elements are 0, coppers are 0. Therefore, I know sulfates from table E are -2, copper is +2, aluminum can only become +3. So you can see that aluminum is going to 0 to aluminum +3, and copper +2 is going to copper 0. Oxidation numbers are changing, therefore electrons are being passed around, and this is a redox reaction. However, there's a quicker way to identify redox reactions. Now, most of them in this course, okay, have a standalone metal or an element. So if you can find one element that is a 0, now that could be an element that's an atom like a metal, or it can be one of these diatomic elements, which we call Hofbrinkels. Okay, remember Hofbrinkels, Hofbrincl. All these guys love to bond with themselves. So these guys, if they're bonding with themselves, they're also going to be, okay, or have a zero. So elements that bond to themselves or elements that are just hanging out, okay, the protons equal the electrons and they're zeros. Now the point I'm trying to make here is if you can find one of these elements in a reaction or 1 0, as I tell my students, you know you have a redox reaction. Why? Because if it's a 0 here, it's something other than 0, which means the charges are changing, electrons are flowing. If something becomes a 0, when it's bonded, it's something other than 0, and again, the charges are changing, electrons are flowing. This is a redox reaction. Please do not say reduction or oxidation. You can't have one without the other. This is total reaction. There's reduction and oxidation. So you could say oxidation reduction reaction or redox would work fine here. So in 52, redox works for me. Certainly you could put oxidation reduction reaction. Don't put one or the other. Okay? You could also say single replacement. That would be acceptable as well. I'm sure there's some other things that I'm not thinking about, but those are the things that come to mind. Okay? Number 53. Number 53, balance the equation in your answer booklet using the smallest whole number coefficients. Okay, so let's go to the answer booklet. So we're balancing that reaction. Now we could write half reactions and balance the electrons, but it'd be much simpler to do it by looking at the mass on both sides. 1 aluminum here, 2 aluminum. So I'm going to put a 2 here. I have 1 copper, 1 copper, 1. Now I'm going to use a little, I'm going to keep the sulfates together. Since I have 3 sulfates here, and it's a little trick we use, not really a trick, but when you're balancing polyatomic ions, it's a nice, easier way to balance is by keeping the polyatomic ions together. So there's 1 sulfate here, okay? And I have 3 sulfates here. So to balance that, I'm going to put a 3 here. Okay, that gives me 3 coppers, and I'm balanced. If you try to break apart, okay, the sulfates, you certainly can and it will work fine. But if you notice, if you keep the sulfates together, it makes life a little easier. 1 sulfate, 3 sulfates. So I put a 3 here, 3 coppers, 3 coppers. I'm completely balanced. You can put the 1 here if you'd like, or leave it alone. It does not matter. Okay, so number 54. 54, explain why the equation represents a chemical change. Okay, all right, so why is that equation that we were given, and that's the equation right here, why is it a chemical change? Well, chemical changes mean that we're creating a brand new substance. So we're starting with aluminum and copper sulfate. These react because it's a chemical change, it's a chemical reaction, and that reaction is going to make brand new compounds, or elements in this case. So it's a chemical change because we are making brand new, okay, compounds or chemical substances. So there are new chemical formulas being made. We started with aluminum. We're ending in copper sulfate. I'm sorry, we're starting with aluminum and copper sulfate. We make aluminum sulfate and copper. So let's go back to the answer booklet and write that. So chemical changes are where you're making new formulas in your products because chemical bonds were broken and new chemical bonds were formed. So many ways to write this, but I kind of like that. So I would say that new chemical bonds were formed. Okay, and thus the products have different chemical formulas than the reactants. Chemical changes are creating new chemicals, okay, from the reactants by breaking bonds and forming new ones. Okay, number 55. 55. Determine the total mass of copper produced when 108 grams of aluminum completely reacts with 9.58 grams of copper to produce 6.85 grams of aluminum sulfate. Well, this is a stoichiometry problem, and they're starting me with 1.08 grams of aluminum. Now, I certainly could take these 108 grams of aluminum, convert that to moles, and then do a ratio of aluminum to copper. Now, we know that this is balanced. Okay, this is 2 aluminums, this is 3, and 3 coppers, and I could do a ratio of moles here. However, look what they gave you. They said that 1.8 grams of aluminum reacts completely with 9.58 grams of sulfate. So if these are reacting completely, the total mass on this side is 9.58 plus 1.08. Do the math, 16, 6, okay, 10.66 grams completely react. Well, law of conservation of mass states that we have to have, guess what? 10.66 grams on the product side. All right, but they said they're producing 6.85 grams of aluminum sulfate. So if I'm producing 6.85 grams of aluminum sulfate, okay, then gosh darn it, what's left over has to be the copper by law of conservation of mass. So 6 minus 5 is 1. Okay, there's an 8. 3.81 grams has to be the copper here, okay, in order for law of conservation to work. So this is 3.81, this is 6.85, and all the mass on the product side has to equal all the mass on the reactant side. That's all that question was. So 3.81 is a question. Let's go to our booklet, and we put that there, although I forgot what I put. So 3.81 grams, just law of conservation of mass. Okay, question 56. Write the chemical formula for the solute in the solution. So a little blurb here. We've got 1.4 moles of sodium nitrate dissolved in enough water to make 2 liters of an aqueous solution. The gram formula mass of the sodium nitrate is 85. So they want to write the chemical formula for the solute. So if I look at the solute is the sodium nitrate that is being dissolved, right? The water is the solvent. So they're kind of talking about, hey, do you know, or they're testing your knowledge of your vocabulary of solutions. So this is dissolved, and you should know that sodium nitrate, sodium is +1. Nitrate, if you did not know what a nitrate is, we need to go to table E. There is table E, which I like to call what the heck is that table, because sometimes you'll see things you just don't know what they are. Okay? So we go to the what the heck is that table, and we'll see that we have a nitrate, and nitrates are right here, and this whole cluster, this polyatomic ion, this N bonding to O covalently, needs an electron to make that stable. So this whole cluster is -1. Okay? So nitrate is NO3, -1, and it's a 1-to-1, so it's NaNO3. However, okay, we have to, I would suggest you put, because it is dissolved, it's a solution, we write aqueous. So I would believe that you would need to have the sodium nitrate aqueous there. Alright, so our formula would be sodium nitrate, so 1-to-1, Na plus to NO3 negative, and I would believe they would want the aqueous there to show that you just made a solution. However, looking at the New York State standards, you wouldn't have to have this. So although I would require this, the New York State Regents does not, so NaNO3 is good enough for them. Okay, moving forward to number 57. Alright, number 57 wants to know the numerical setup for calculating the mass of the solute used to make the solution. So let's get some things out of the way here. All right. So we want to calculate the mass of the solute. So what do they give me here? Well, they're giving me 1.4 moles of sodium nitrate, and they're giving me 2 liters of the solution. Okay. So we know that molarity is equal to moles over liters, right? And they want to know the mass. So I don't need all of that. So they want the mass of the solute. Okay, so molarity is moles over liters, but they just want the mass. So all I have to do here is take my 1.4 moles that gets dissolved and convert it into grams. So I know I just said that. We don't need that. Okay, however, all this question is about is converting the moles into grams. So let's show that work on our, at least show the correct numerical setup. So they don't want the answer here, they just want the setup for the question. So we'll do that on the answer booklet. Now before we go to the answer booklet, we should see that there's some pieces of information we need. We have 1.4 moles of our solute, and we have 85 grams per mole. They're giving me the formula mass. All right, they're giving me the gram formula mass, the grams per 1 mole. So that's given to me already. Okay, it's kind of nice. So let's go to the. All right, so we want to convert we want to convert 1.4 moles of our sodium nitrate into grams. And as we've taught you, using dimensional analysis, we can get rid of the moles. For every 1 mole, there's how many grams? Now, if we didn't have a formula mass, we'd have to add all this up, but they gave this to us, 85 grams. And that's the setup. If you want to answer the question, you can, but they're just looking for you multiplying 1.4 times 85. They don't necessarily have to have this canceling out. They would accept all different kinds of things as long as you show 1.4 multiplying by 85. Okay, that would all be acceptable. Of course, with those studying chemistry, okay, you know, I would guess that you would write something along these lines. But 1.4 times 85, something along those lines is the answer. Okay. Number 58. Compare the boiling point of the solution at standard pressure to the boiling point of the water at standard pressure. So what we're doing is we're going to compare the solution, its boiling point, when you have solute particles mixed in the water, and we're going to compare it with pure water. So we're comparing water, or the solution, with the water. And as you know, as you add solute particles to the water, it's harder for the water to circumvent them. It's a colligative property, okay, concept. So if these little blue circles are my water, and these red ones are my solute particles that are being dissolved. This is a homogeneous mixture, okay? It's harder for the water to get to the surface, okay, because these solute particles are physically in their way. So because they have some obstacles, okay, in order to get to the surface, if they have enough energy to overcome their attractive forces, okay, their vapor pressure has been lowered. And therefore, if their vapor pressure is lower, okay, boiling is going to need a higher temperature. Remember, boiling is when the vapor pressure upward equals the pressure pushing down. And guess what? If the vapor pressure has been lowered, okay, the pressure pushing down is now higher, you're going to need a higher temperature to give these water molecules enough energy to get around those obstacles. So the boiling point is elevated. Boiling point elevation, freezing point depression. Okay, I have a thumbs up sign in my class I use. Okay, it's a sign we get into the chemistry party. A thumb goes up. I can't really draw really well, and a thumb goes down to signify the higher temperature always rises when you add solute particles, and the freezing point depresses. Now, they didn't talk about freezing point, but who cares? So the boiling point of the solution is higher than the boiling point of standard solution. Let's go. Okay, so the boiling point of the solution is higher than the boiling point of the pure solvent. Okay, now when you're answering these types of questions, make sure that you answer them based on what they said. Let's go back to you have to pay particular care to how they want you to answer the question. They want you to compare the boiling point of the solution to the boiling point of the standard. So I would answer the same way. The boiling point of the solution is, of course, going to be higher because of boiling point elevation, and the boiling point of the water, the solvent, is lower. Okay? Should answer exactly how they ask it. Very important. All right? So we're going to move on to number 59. 59 states, okay, what is the molarity of the solution? Now I get to use my molarity formula that I was so eager to use before. Molarity is equal to moles over liter. And if you do not know this, okay, let's go to table T. It's listed for you. Here is table T and all the important formulas and questions, your last table. And if you notice, you're going to have a concentration. There's your molarity formula right there, okay? Just to remind everybody, moles of solute, that's in this case the sodium nitrate over the liter of the entire solution, and molarity is a quantitative type of number that describes how concentrated or dilute you are. Let's go back to the problem. So they want to determine the molarity of the problem, okay? So all we need is the moles and the liters. Well, guess what? We have those. So we know from the information given to us, we have 1.4 moles, and we know that we have 2.0 liters. That equals my molarity. We'll put that in our calculator, okay, and 1.4 divided by 2 gives me 0.7. Now I would probably write that, okay, 0.70 molar. Now they did not say with the correct number of sig figs, so they probably would accept, okay, 0.7, all right. But you should know that this has 2 sig figs, this is 2 sig figs. Good practice to use 2 sig figs. So the answer is 0.70. Okay, let's go put that into our answer booklet. 0.07 molar. Notice they're putting a unit for you there. So right or wrong answer. Number 60. Okay, so they have a little blurb here. Sometimes it's very helpful, sometimes it's a lot of information. I tend to go to the question first and see what information I need. A lot of my students tend typically reading these long-winded ones, and this is not a long-winded one, but sometimes these little blurbs here in the part 2 section get so long-winded that people tend to get like psyched out before they even read the question. So my suggestion is, and certainly go what your teacher says, read the question first and then go back. Compare the electrical conductivity of the aqueous product. Aqueous product is the calcium hydroxide. Now they said aqueous, so they're talking about some free ions, right? This, although they write it together, is really free ions. Aqueous means you have calcium plus 2, and you have hydroxide ions that are free to move in that water. Now, you're comparing how well they conduct, and you should know that free ions are electrolytes. So this is a good conductor, all right? All right, and to the what? I'm comparing how well this conducts to the electrical conductivity to the white solid that remains after the water's evaporated from the solution. So if you were to take out the water, and you would actually recapture the salt. So you have in a beaker with water calcium plus 2 and OH minus. You boil off the water, you're going to be left with a beaker of a solid. And you should know that positives and negatives make something called ionic compounds. And ionic compounds, okay, only conduct in a liquid state that gives them free ions, or it conducts, okay, in an aqueous state. Both the aqueous state in a solution like we have here, or if you heated them to a liquid, conduct, because that would give you, okay, free ions. But if they're in a solid form, those ions are basically locked in a three-dimensional crystal called a crystal lattice. The positive attracts the negative, and it goes in 3 dimensions. Okay, and those ions are not free in a crystal. So very clearly, the electric conductivity is high for the free ions, but essentially 0 for the ions that are not free in the solid. So let's put that in the booklet. So I said the free ions in a solution are a good conductor, but the solid is not. They didn't ask for why. I'm kind of giving you why and giving the opportunity to teach. I'll jump in there. Now, with all of these free response explanations, they're going to accept many different ways to say the same thing. So they'll say acceptable responses include, but not limited to. And that's what I mean, is that You can say this many ways as long as the chemistry is right. This is the way that I phrased it. If you use the same thing but a different way, that is fine. Okay, number 61. 61, write the chemical name of the base produced. Now you should know that the Arrhenius definition of a base is a hydroxide. So you should know that that's clearly a base. Besides, if you did not know that, you could look somewhere in your reference table to remind yourself what a base is. And here is table K, which reminds you what acids look like. H is in front. Usually they give off the H's and bases. And lo and behold, look at that. Calcium hydroxide is in fact the base that's listed in the reaction. And of course it reminds you that some bases have hydroxides, which is the Arrhenius definition, and of course this one is the a base based on the Bronston-Lowry definition. It can actually accept, okay, H plus is because of the lone pair on the nitrogen. So yeah, it's already listed there as calcium hydroxide. So calcium hydroxide. Now you certainly could have used the chemical formula and said, oh, CaOH, and you could actually have used table E, what the heck is that table, and seen that this was a hydroxide, and by the IUPAC naming system, okay, our IUC, calcium hydroxide, okay? Any case, 62. Okay, 62, state one change in the reaction conditions that will increase the rate of the reaction. Okay, well, we know the factors that affect the rate of reaction are manyfold. Okay, you can increase the concentrations, but they want one change in the reaction conditions. So you can actually pick probably any of the following types of factors that affect reaction conditions. You could increase the concentration, okay? Now, we can't really increase the concentration here because this is a solid and this is pure water. But we could somehow increase the number of available atoms to make effective collisions here. One way we can do that is we probably could increase the surface area. So if we had lumps of calcium and we had powdered calcium, that increase in surface area allows more calciums to be available for collisions, therefore more effective collisions. So surface area is a good one. Or, you know, you could do temperature. Temperature, of course, gives more motion to these particles, therefore the number of collisions increases, and thus the number of effective collisions increase. And those seem to be the ones that are most common. So to our booklet we go. Okay, so you could have picked increase, an increase. I can write in temperature. They didn't ask for why. You certainly could say an increase in surface area, and those are two examples, but it's not limited to that. If there's some other things that make sense, that could possibly be right as well. Okay? Again, the nice thing about these part 2s, you're not locked into just one answer. There's many ways to explain the correct chemistry. That's why I consider these questions actually easier than the multiple choice. Number 63. All right, this next question, we have a titration with hydrochloric acid and with a base. Number 63 says, complete the equation in your answer booklet for the neutralization reaction by writing the formula of each product. Okay, let's go there. Now, acid-base reactions are called neutralization reactions, and by the way, they're very similar. They are, in fact, double replacement reactions. The K is plus, the hydroxide's negative, the proton is positive, the chloride is negative. So this positive will find this negative and make KCl. And this OH minus finds the H plus, right, and makes the HOH, which is water, or you can write it H2O. It's a double replacement. So neutralization reactions are nothing more than double replacement reactions, but you could also remember that an acid plus a base gives you a salt and water. All right? So that's it, and of course I don't think they asked for it to be balanced, but it is balanced anyway. 64. Number 64, compare the number of moles of H plus ions to the number of moles of OH minus ions in the titration mixture when HCl is exactly neutralized. Well, neutralization, guys, okay, is when the protons from the acid are absorbed by the bases to make water. You no longer have a basic or acid there, you have water. So neutralization is happening. If you notice, it takes one H plus to one hydroxide to make water. So all they're really asking here is that when something is neutralized, what does that mean? It means that the protons equal the hydroxides. And that's it. You look at this question, you might say, well, aren't they asking for exactly how many? They want to compare the number of moles, okay, of OH ions to the, compare the moles of H plus ions to the number of moles. They have to be the same if they're exactly neutralized. That's all they wanted. They didn't ask for the exact numbers. Okay, so to the answer booklet. So the moles of H plus are equal to the moles of hydroxide. That's just it. Okay? 65. So 65 says determine the concentration of the KOH. Well, this is a titration problem. In a titration problem, we use something called a titration formula called MV of the acid equals MV of the base. Something you don't have to memorize because in table T, as I will show you, it's there. Table T we go. There's our table T. And let's go down to titration, and there it is. The molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. And that's what we use to solve for the unknown variable in this 3-variable question or 4-variable question. Okay, so yeah, you have 4 variables, molarity is involved, and volume does not have to be in liters here. Given 3 out of the 4, we solve for the unknown. So that's our equation. Back to the problem. Oh, our acid is HCl. I'm going to write that because I want to pay close attention to how many H's come off. So there's only one proton that comes off per one of these molecules. And the base, okay, is KOH. And there's only one hydroxide that comes off per one of them. So we're good. This is a 1-to-1 scenario. Sometimes we may have different numbers of hydroxides and protons matched up, and we have to make an adjustment. Here we do not. But you should evaluate that before every titration problem. So the molarity of my acid, okay, is what we're looking for. No, we're looking for the concentration of my the base. So our unknown is this right here, the molarity of the base. That's our unknown. What are we given? Well, we're given the 0.5 molar hydrochloric acid, so 0.15 molar. The volume is 20.0 milliliters. And the volume of the base that was needed to neutralize that acid is 18. So now we're going to solve for M. And M is going to equal to, the molarity is equal to 0.15 molar times 20.0, let's just write this a little better, okay, 0.15 molar, okay, times 20.0 milliliters, putting the units into volume, over the 18.0 milliliters, and you'll see that the milliliters cancel, and you're left with molarity. Put that in our calculator, and we get 0.15 times 20 divide by 18, and we get 16.7. I mean 0.167. Okay, sorry about that. And that's the molarity. And let's do sig figs. 2 here, 3 here. They're not asking for sig figs, but it's just good practice. So 0.17 molar is our answer. Straight plug in with our formula from table T. We kept track who was an acid and base. We plugged in, did our math, and we got our answer to 2 sig figs, even though they're not asking for them. Okay, let's put that into our answer booklet. 0.17 molar. Okay, and number 66 is next. Okay, so part C is where we're starting now on number 66, and this is a little more descriptive, okay, in the amount of information they give you. And as I told you before, I find it a good strategy is to go to the question first and see what they want, because at the end of the test you might be tired. Some of my students get intimidated here. So there's a lot going on here. John Dalton's an early scientist. Okay, he sketched compounds using his own symbols for atoms, and there we have a symbol for something there with that key. They give you some more information about the the hydrated compound. Any case, let's go to the question. A lot of information here, and a lot of times, a lot of it's not even used. And a lot of times you have to go back and reread it to get what you want. But don't let this intimidate you. Go right to the question. That's my suggestion, but go do what your teacher says. 66. Identify one positive ion in the hydrated compound. Your response must include both the chemical symbol and the charge of the ion. So if I go back up here, and if I didn't know what was going on here, there's a sketch here. Dalton's for 4 elements of his drawing. So Dalton had a drawing of potassium aluminum sulfate using his symbols. Okay, so the question reads, from this sketch and using this key which represents these elements, what is one positive ion? Well, I know metals, okay, I should know metals love to lose electrons and oxidize and become positive ions. So I'm looking for a metal here that became a positive ion, as they all do. And I can see that I have potassium and aluminum are my metals. So if they're involved in this structure, okay, they're not zero, right? Elements that by themselves are zero. So if they're bonded to something, they have to have an oxidation state other than zero, and it will be positive. If you're not sure, okay, let's go to the reference table. Okay, let's go find aluminum. Aluminum's right here. Okay, what charge does it like to become? And it is +3. Okay, all metals become +3 or plus or positive because all metals lose. Look at all these metals here. Okay, and for those that don't know, the metals are below the staircase. All of these guys here are positively charged because they all like to lose electrons because they don't hold on to them. That's what makes a metal have its properties, or one of the major properties of metals is they lose electrons. So in any case, potassium becomes +1. So you can put down either potassium or aluminum. So I write aluminum +3. I don't write or here because I'm just showing people that you could have also picked potassium +1. Those are the only two metals, and these are its appropriate charges, +3, okay, or +1 for this other atom. So that's important that you got the right charge, and we get these charges in the reference table if you did not know them already, and they only had one choice. Okay, so 67. Describe in terms of composition one way in which Dalton's perception of potassium aluminum sulfate differs from what is known today about the compound. All right, in terms of composition, you have to answer questions based on how they are asking them. They're telling you you need to ask in terms of composition. Composition means how it's made up. So we're going to have to compare Dalton's perception with the current. Okay, now composition. Let's look here. We have a potassium in the middle. We have this aluminum. There's, according to him, 3 aluminums. Okay, each aluminum has a sulfur and 3 oxygens. So looks like to me SO3s are involved. Okay, so it looks like you have every aluminum has an SO3, and there's another SO3. All right, SO3. Okay, and then if this is the aluminum again, and let's get rid of, okay, aluminum and another SO3. Sulfite ion, according to him. Okay, so if we look here, it looks like to me you got 1, 2, 3, 4, 5 sulfite ions involved, and here he's got sulfates. Okay, so according to the structure that Dalton drew, he's got a lot of SO3s here. Okay, now what else does he have? Well, he has 1, 2, 3, 4 aluminums. Okay, and well, he's got, okay, we got 1 aluminum. All right, so, and there doesn't seem to be any water. So there's many ways you can go about doing this, but what's the question? In terms of composition, one way which Dalton's perception of potassium aluminum sulfate differs what's known today. Well, he has 1 potassium for 4 aluminums. I could state he has more aluminums. He also has more sulfates or sulfites, SO3. So many ways to go about this. Let's go to the answer booklet. So Dalton's drawing had more aluminums. Okay, you could leave it at that. And again, there's many ways you can answer this. Going back to his diagram again. So I said, you know, hey, aluminums are here, and I've got 1, 2, 3, 4 aluminums, and the actual compound's got 1. So that's the way I answered it. You could have said, well, gosh darn it, there's what? 12 waters, and there's no water molecules. Okay? What other way can we look at this? Let's see. This guy's got 24 hydrogens. I don't see any hydrogen here. So all of that could have worked in your favor in terms of answering this. It's not just one way. Again, it's a nice, part twos are nice, I think, and easier in the fact that you're allowed to, you know, use the way you'd like to answer a problem. So number 67 is done, and let's go on to number 68. Show a numerical setup for calculating the percent composition by mass of water in this hydrate. Well, we did a hydrate lab. Okay, the percent by mass of water. Well, we know that it's going to be a part over total times 100. Now hydrates, we care about the water, so it's the part is the mass of the water over the total mass, which is the hydrate, because that's the compound with the water in it, times 100. So how do we do a numerical setup? Well, we have to know the mass of the entire hydrate. Well, let's pick 1 mole, right? So if we just assume 1 mole, okay, so we assume 1 mole, why not? We know the formula mass is 474, and all we need is the mass of the water. Okay, well, we have 12 waters, or okay, per every 1. So if we have 1 mole of this compound, we have 12 moles of water. And we should know that water, okay, is 18 grams per mole. Okay, if you don't know that, you do a formula mass, right, for 1 oxygen, we know is equal to 1 times the atomic mass of oxygen is 16. And for 2 H's, I should say, all right, let me just change how I would do this. I would write it this way. I would say there's 1 oxygen, 1 times 16 is 16, 2 H's, 2 times 1 is 2, right? And I'm getting these numbers from the atomic mass. If you look up on your periodic table, you'll see H has a mass of 1, oxygen has a 16. I'm just adding those atomic masses to get the total formula mass, and I get 18 grams for every mole. Okay? So you put, if 18 grams per mole, all right, we have 1 mole, well, we have 12 times 18. So we take 12 times 18, right, because if in 1 of these, we have 12 of these. So we have to times that by 12, right? So 12 times 18, and you get 216. All right, and then I'm going to put that right there, 216 over 474 times 100, and that's our setup. Okay, so we needed to figure out how many grams were the water, and all we did is we figured out was 12 moles. So if I write this out better, 12 moles of H2, we want to convert that to grams for every 1 mole of water. This is what we figured out. We found a molecular mass. Okay, it was 18 grams for every 1 mole. And that's why we times it together to get 216 grams. And that's how that works. So number 68, 216 over 474. I mean, I like to put the units in. They won't mark it wrong if you don't. And that's it. They just wanted the setup. Now, I got the 216 by converting to moles, but you could have said, you could have made some kind of algorithm like, okay, I know that there's 2 grams plus 16 in 1 mole of water, and I could times that by 12 and then put that by 474. Okay, if I didn't want to do any math, of course, times that by 100, and that would have been acceptable too. It doesn't matter. Okay, 68. Number 69. Okay, so we got another descriptive blurb here. Okay, talking about hydrogen peroxide, and they give me the decomposition of it, and they give me the heat in the product side. I see that it's exothermic, right? Don't know if it's part of the question. I'm just looking at it and see what kind of hints I can get. I'm going to read the question first and go backwards. State in terms of both melting point and boiling point why hydrogen peroxide is a liquid at room temperature. Okay, let's see what they talked about that. Hydrogen peroxide melts at negative 0.4 degrees Celsius. Pretty low melting point. Okay, and it boils, all right, boils at 151 degrees Celsius. High, very soluble. Okay, so why would it be a liquid? Well, if something is a liquid, that means the current air temperature, say temperature, okay, is above its what? Freezing or melting point. So the melting point is here. In this case, it's negative 0.4 degrees Celsius. Okay, so we got a negative value for a melting point. So let's just do that nicer. Okay, so the melting point is equal to negative 0.4, and the current air temperature must be what? Above it. If you're above the melting point, you melt into a liquid. So why is H2O a liquid? Well, the first part is that the current temperature, okay, of the room, and they said standard pressure, okay, they gave me a temperature, okay, it's decomposed at room temperature. So now room temperature, okay, is about 20 degrees Celsius, okay, but certainly it's not going to be -4. So we had room temperature has to be above the melting point. That's the first part. So room temperature has to be above the melting point. Right? Anything above the melting point is going to be melted into a liquid. And if it boils at 151, the room temperature must be what? Below the melting point. Right? Below that melting point. So if we're below the melting point, the boiling point, right? Sorry. Boiling point. So if we're below the boiling point, we're not a gas yet. So room temperature is above the melting point, which means it's melted, and we are below the boiling point, which means we haven't turned into a vapor yet. That explains why we're a liquid. So again, notice how they want you to answer the question of both the melting point and the boiling point. If you just give me one, I have to mark it wrong. You have to pay particular attention to exactly how they want you to answer the question. So let's go to the booklet. Okay, so room temperature is above the melting point but below the boiling point. And that answers the question completely how they want you to do that, because you're talking about the melting point and the boiling point in your answer. Number 7. Number 70, state the evidence that indicates the decomposition of hydrogen peroxide is exothermic. There it is, in all of its glory. Heat is on the product side. Okay? All right, so therefore, you're releasing heat into the environment. Now, I don't know if there's anything else in the reading that could tell you that if you don't like that, but that is clear as day to me that it's exothermic because heat is on the product side. You're releasing heat. Okay? So, back to the answer book. So I wrote, heat is released as shown by the heat placed in the product side of the equation, probably. Of the chemical equation. Or reaction. Okay, 71. Number 71, explain why a hydrogen peroxide bottle needs a pressure releasing cap. Well, There's sometimes these questions are in the reading. I don't see anything here that states anything other than the reaction. And if I look at the reaction, hydrogen peroxide decomposes into more particles of a gas. In fact, we make liquid, aqueous goes to a liquid. I should say that we have aqueous solution becoming a liquid, but we're producing gas. And gas is going to increase the pressure in the bottle, and it's going to take up space above the liquid, which will push up on the liquid and eventually have to be released, because as this continues, if you have the peroxide long enough, okay, the amount of oxygen produced is going to increase the pressure so much you could have a bursting of a bottle. Okay, so the answer is you're producing a gas, and a gas is going to increase the pressure as this breaks down. So we have to alleviate that pressure to prevent, let's say, an explosion, or at least a release of perforation. Okay, to the answer booklet. Okay, so I said the oxygen that is produced will increase the pressure continuously as the H2O2 decomposes. This increase of pressure could burst the container. I mean, you could say so many different other things that is that's correct. It's on point. So acceptable responses include, but not limited to, many different ways. So when we grade these, we take anything that is correct. So you don't have to say this exactly. But along the lines, as you're producing a gas, the pressure is increasing. If we don't have a pressure releasing cap, you know, the bottle could be perforated, those kind of things. Number 72. Number 72 has a voltaic cell diagram like in this so far. Okay, little blurb here, student constructs an electrochemical cell, switch is closed, electrons flow through the external circuit, diagram and equation below. Okay, so this is just a straightforward problem, and the first thing I do with any voltaic cell, and I know it's a battery, a voltaic cell, because I see a salt bridge. Okay, the first thing that I do before I do any questions, I look at my electrodes. I have aluminum and nickel, and I want to evaluate who my anode is. Once I can do that, all the rest of these problems make sense to me. So the first step, between aluminum and nickel, who is better at oxidizing? So I go to table J. The absolute first thing you do with a battery diagram, a voltaic cell, is you got to go to table J, and you got to know who is being oxidized the best, because the one who's oxidized the best, the higher on table J, you're going to find yourself the anode. So we're looking for the anode. So let's go to table J. So here's table J, and we're looking on the metal side. The most active metals are the ones who lose electrons the best. That's what metals do. They're big, they lose electrons. Electrons are held loosely. We're going to see who loses the best, who oxidizes, Leo. So I've got nickel or aluminum. Here's aluminum. Aluminum's up top here, and nickel's way below. So of the two metals, aluminum clearly is better at oxidizing. And we know that oxidation, Leo the lion says grr. So losing electrons, oxidation, aluminum's better at oxidizing. And you should know and what? And ox red cat. Anode is the who oxidizes. So clearly aluminum is my anode. So there's my anode right here. And here's my cathode. And I know, once I know who my anode is, electrons always flow from the anode to the cathode. Always flow from the one who oxidizes, loses electrons, to one who what? Gains electrons. It can only be that way, guys. You can only have someone lose electrons to someone who gains them. That's how the flow always goes. This is always the case in every diagram. So the first question, state the direction of flow of electrons through the wire when the switch is closed. It goes through the aluminum. It goes from the aluminum to the nickel. Do not tell me that it goes to the nickel plus 2. All right? Electrons flow from electrode to electrode. Okay? They don't flow off the electrode into the ions, because if you know, you have nickel plus 2 here. And this nickel plus 2 is going to accept these electrons, okay, that came from the anode. This is going to go toward it. So electrons don't flow through the solution. So this nickel plus 2 gets reduced, as the overall diagram shows. Okay, so we go to our book. Electrons flow from aluminum to nickel. I guess you could also say they go from what? Left to right. I would like this to be the best answer, but I think they're accepting left to right as well. You cannot put nickel plus 2 here though. Okay, electrons go from electrode to electrode. Number 73. Write a balanced half reaction equation for the oxidation that occurs when the switch is closed. Well, they made life real easy for us because they gave us the overall reaction. I never would have, but we know that the anode is over where? At the aluminum. So the aluminum is going to oxidize, and when it does, it becomes aluminum plus 3. How do I know that? Because aluminum only becomes one choice, plus 3 electrons. Now, they kind of cheated and gave you the overall reaction. There's a 0, there's a redox reaction, and there's aluminum plus 3. So they just want the balanced half reaction equation for the oxidation that occurs. So I've got aluminum. It's going to aluminum plus 3. And I know that because I see the charge there. So I'm just taking out the aluminum on the reactant side. And on the right side of the arrow, I have aluminum plus 3, just taking out 1. And to balance this, you have to balance the mass, one aluminum, and you got to balance the charge. So we have 3 electrons. Negative 3 and a positive 3 gives me 0 on this side, and this is 0. Now some students would say, well, wait a minute, isn't there 2 aluminums involved? So you put a 2 here, a 2 here, 2 times plus, right? If every aluminum is plus 3, then that gives me a plus 6 overall. I would need 6 electrons. Believe it or not, they will take the one with just either 1 or 2. Okay, so they took that either it was balanced in the equation or just took it out. By saying balanced, okay, they could just meant the charge. So to the booklet. So an aluminum at the anode becomes aluminum plus 3 and gives off 3 electrons that travel through the circuit to the cathode. Okay, whether you write it that way or you write it this way, according to the Regents people, this is correct. Okay, back to number 74. Determine the number of moles of aluminum needed to completely react with 9 moles of nickel plus 2. Okay, this is like a stoich problem, okay? Moles of aluminum. Okay, let's think here. Let's get some stuff out of the way. Moles of aluminum. All right, with 9 moles of nickel. Let's look here, guys. They want to ask about how much aluminum is needed to react with 9 moles of nickel plus 2. What's the ratio? There are 3 nickels for every 2 aluminums. So I think of it this way. You have 9 moles of nickel plus 2. You want to get rid of nickel plus 2, right? And there is what? 3 nickel plus 2s for every 2 aluminums. And when we cancel, nickel plus 2 goes bye-bye. And I'll just get moles of aluminum. Since it's really going from moles to moles, it's a stoich problem. And we're going to use the what? The coefficients as a mole ratio. So 9 times 2 is 18. 18 divided by 3 is 6.0 moles of what? What's left over? Aluminum. Now some people don't like this method because of many different reasons. But at this point, let's make sure we know how to do this. Watch. If you have a mole-to-mole problem, here's what you can do. This is my x, and I know I have 9 here, right? Coefficients become the denominator. That becomes 2. This coefficient becomes the denominator is 3. And I have x over 2 equals 9 over 3. And I solve for x, and I'll get 6 as well. Okay? Either way, 6 moles of aluminum is needed. Let's go to the chart. Answer booklet. 6.0 moles, and again, significant figures were not asked for, so they're not grading it based on that. So you put 6, perfectly fine. Number 75. Okay, number 75. Here we go. State in terms of energy why this cell is a voltaic cell. Okay, well, voltaic cell, as Alessandro Volta and Luigi Galvani came together with that discussion, but it's a voltaic cell because it is spontaneous. Okay, it produces energy. All of that would apply nicely. to explaining why this is a voltaic cell and let's say not an electrolytic cell. So you would say that this cell is spontaneous and thus does not require a battery. It produces electrical energy. Many responses you could say that explain why it's a voltaic cell. The easiest is, hey, it's spontaneous. It produces energy. Okay, it converts chemical energy to electrical energy. Many ways to say this. And that's why part 2 is a great thing, because you're not locked into one answer. Okay, number 76. Okay, number 76. Looks familiar, doesn't it? Which labeled part of the digestive system has the most acidic environment? Okay, if you're very acidic, as you should know, your pH is lower. Okay, it's low because your H plus ion or your hydronium ion concentration, okay, is very high. For instance, it could be 1 times 10 to the negative 2. If it's low, it could be like 1 times 10 to the negative 8. This is a bigger number. The pH, as you've learned, is the negative log of this exponent, which in all intents and purposes, if there's a 1 in front, it's the positive value of this exponent, so the pH is 2. So as your pH number decreases, this number becomes a smaller negative exponent, which means a bigger number. In any case, the most acidic part of the digestive system, of course, the lowest pH is the stomach. Stomach. Number 77. Okay, number 77. What is the color of thymal blue at the pH of the small intestine? pH of the small intestine. Okay, let's read. pH of the small intestine is 7.3. So 7.3 is our pH. I don't know what thymal blue is off the top of my head, but I do know where to look, and that's reference table M. Okay, so reference table M, I'm looking for thymal blue, and if it's 7.3, okay, thymal blue, all right, is, well, we know that everything 8 and lower is yellow, and 7.3 is lower than 8, so it has to be yellow. If it was 9.6 or greater, it would be in the blue range, and things in between would be green. So we're in this range in front of 8, less than 8 would be yellow. And there we go, yellow. Number 78. State how the catalyst lipase increases the rate of fat digestion. Okay, well, how will lipase increase the rate of fat digestion? This sounds like a biology question, but what they're getting at is we've got a catalyst. And how do catalysts work? You should know they lower the activation energy, or they find an alternative pathway. Think about a potential energy curve. A catalyst creates an alternative pathway. Doesn't change the energy you start with and the energy you end with, but it lowers the energy you need to get to the top for the reaction to occur. The analogy I always use, if you want to ride the slide, you got to get to the top. Well, it makes less energy. So the activation energy, EA, for those people who took a high-level course, the activation energy is lowered, okay, by finding an alternative pathway. 78. So it lowers the activation energy. That'd be sufficient. You can say it again, finds an alternative pathway, all different things you could say, but those are the two major things you should keep close to your hip in terms of how to answer why a catalyst speeds up the rate of reaction. 79. Okay, identify the type of reaction used to make soap. That's saponification. Okay, and that is essentially what you're looking at. Okay, you're making a soap molecule right here, alcohol. All right, and you're cleaving this this ester to make a soap molecule. Okay, with a nonpolar ending, hydrocarbon, very symmetrical. Okay, and a polar end. Any case, saponification. Let's go to the booklet. There it is, saponification. Cleaving a fat or an ester in a fat into the soap molecule with a polar and nonpolar end. Number 80. To which class of organic compounds does ethyl stearate belong? Ethyl. Well, what is this? This is the rest of an organic molecule. You can write that R. It's bonded to a C, double bonded to an O, bonded to an O, bonded to another rest of an organic molecule. This is the general formula. We have something called table R, okay, that we can go to see what that is. Let's go there. Table R, functional groups is the class of compounds. Let's go find our general formula. And I think I found it. I think you have too. Okay, now that you know where to look, and there's the R, C double bond to an O, to an O, to an R, and this is an ester. Okay, that's the class of compounds. Remember that YL ending. They use a different ending, but it's the same thing. So this is an ester. Number 81, identify two types of bonds in the compound sodium stearate. So sodium stearate, okay, right here. Now you could say a couple of different things. It's a pretty vague question, but you could say single bonds, you could say double bonds, you could say, hey, covalent between the C and the O, share electrons, but ionic between the negative O and the positive ion. Okay, those are the best ones that I could think of. So covalent, ionic, but again, you could go polar, you can go double or single bonds. This is the best answer, I think. Number 82. Okay, so we've got a little blurb here about some information that we may or may not need, and here's some nucleides used in nuclear reactions. This is a fission and fusion type of reaction. Compare the atomic masses of nucleides used in fusion, that's making molecules come together, and then of course compare them to fission, which is splitting the atom. Now notice how they worded it. Compare the masses of used in fusion to fission. So these guys, the masses are lighter. The nuclei are smaller than the ones we try to split in fission. It's just that simple. Okay, let's go to the booklet. So the nucleides in fusion are lighter than the nucleides in fission. I mean, it's almost as if there had to be more to that question, but don't overthink these questions. Number 83. Complete the table in number 83. Complete the table in your answer booklet that compares the total number of protons and the total number of neutrons for the hydrogen nucleides used for fission. So let's go there. All right, well, I know that hydrogen 1, top number is the mass number. Bottom number is the atomic number. Now, how do I know that? Periodic table tells me that. Let's go there. Looky here. Mass number, top number, atomic number. This is the number of protons. This is the number of protons and neutrons. Why? Because a proton and a neutron have the same mass if you check out table O. Okay, back to our problem. So our proton number, which identifies the element, is 1 for both of them. Okay. Number of neutrons, well, 1 minus 1 is 0. Remember, this is the proton and neutrons. This is the proton. Subtract, you get neutrons. So this is 0 neutrons. And this is tritium. It's the name of the isotope of hydrogen with 2 neutrons. How do I know it's 2? 3 minus 1 is 2 neutrons. It has 1 what? It has 1 proton. They both have 1 because they're both hydrogen. Number 84. Number 84, complete the nuclear equation in your answer booklet for the fission of 235 by writing notation of the missing product. Let's go there. Okay, well, we have to have conservation of mass and conservation of charge. So, the total mass number, all the top numbers here, 235 plus 1 is 236. Okay, this has to be 236 on this side. Okay, so if you think with me for a second, we have 142, so this whole thing has to be 236. All right, so 142 and 91, you add them together, 142 plus 91, you get 233. We're 233, so we need 3 more. Right? This being 233, we need 3 more to make this 236. Since there's a 3 in front, each one is going to have a 1. Right? And then check out the bottom numbers, the charge number. 92 plus 0 is 92. Okay, we add these together, and 36 Okay, 56 and 36. Okay, gives me a 12. 92. Whoa, it's the same number. If that's the case, then this number has to be a 0. And what particle has a mass of 1 and no charge? Now, if you're still stuck, let's go to table O. Table O has a mass of 1, no charge. Of course, that's a neutron. Let's go back to our... And there it is, my neutron. Okay, you need that little N there. Besides, if you look at this carefully, this is nuclear fission. It splits apart into smaller particles and it produces 3 more neutrons, if you remember that. Number 85. Number 85. State one benefit of using nuclear fusion instead of the current use of our nuclear fission to produce energy. Currently we use nuclear fission. We split the atom in our nuclear reactors that we use nationwide. We would love to go to nuclear fusion. Supposedly we have Lockheed Martin making one. We'll see. Okay, what's the potential of nuclear fusion? Well, gosh darn it, there's more energy released because there's more missing mass and mass defect, but there's more energy. Okay, also it's cleaner in the sense that there's no radioactive waste. Okay, I'll put that on the sheet for you. And I wrote fusion produces more energy per same amount per gram, or you could say that there's less radioactive waste, you know, and there's an unlimited amount of fuel for fusion if we're going to use hydrogen. There's plenty of hydrogen from the water on its Earth. Many examples you can write here, and there's some here that I'm probably not thinking of that'd be correct. So, any case, that concludes the Part 2 section, the free response section, which is 35 points. And I hope you enjoyed and got something out of this review. Take care.